Hello, I'm happy seeing you. It was like 5 minutes before and nobody was here. So I thought, oh, maybe I'm going to give the class to myself. Okay, so let's just start with some announcements. First of all, sadly, there will not be a TA session today, or actually a live TA session for miscommunication between me and my TA. Let's just not go into detail why, but essentially SETI is going to record the TA session and post it on Moodle later. But anyways, so I just posted the solutions and really to make sure that there's no problem for you. If you have any question or uncertainty about how one or the other problem are solved, then please email me, come to the office hours, or even if there's really, you cannot come to the office hour, email me and I can schedule another time for you to explain you some detail about how we do it. So yeah, sorry about that. So that means only 4 hours or only 3 hours of math today instead of 4. Too bad, but that's the way it is. I would gladly do it, but yeah, the thing is I have to get ready super quick for the next class I give in the afternoon at Concordia. So yeah, I don't have time to do it. So that's this. Now I've received an email from somebody who asked what program am I using to draw graphs in class. Yeah, let me just tell you a bit. Well, I'll just show it to you actually. So what I do is I generate some blank PDF. So just a blank page, a blank PDF page, nothing special about it. And let me share my screen. Yeah. So I just opened this blank PDF page and it's called, so the program is called PDF Exchange Viewer. It's free. It's something everybody can download. It's usually just a viewer, but I have tweaked it a bit to help me teach. So one thing that's pretty neat is you have some shortcut on the keyboard that allows you to show a grid. So then I can show it or not show it. And then here I have some drawing bar that allows me to put comments and stuff. So, or just typewriter, which I use to annotate the PDFs. Or here you can have a box around it. And especially the nice thing is these are all tools that I designed for myself. So I can add some other type of line that's preset with the color preset and everything preset. So it makes my life easy to do things. So I'm pretty sure I'm the only person in the world who's using this. Probably other people use other things. Maybe I'm not going to use this for the best graphs possible, but it does the job for the class. And it's quick, and I can, generate a PDF and then start drawing on the PDF. So that's a neat thing. So if you like, it's PDF Exchange Viewer. And the thing I use for math, which I'll go back to, is this thing, Scientific Workplace. So that's something that it was the glory days back in maybe 10, 15 years ago. But now it's rather shameful to be telling people you're using Scientific Workplace. Normally you would use LaTeX or some other program. But I find it super convenient because you have all these tools, these compute tools. So if I have matrices, I can basically compute whatever I want with my matrix. So yes, it works very well as an editor too. And now I think the company went bankrupt, but what they're trying to do is to release the program as open source so that people can start working on it and improve it. So that would be awesome if they do that. All right. Okay. So yeah, I think I said that you had to give your assignment today. I hope everybody did. I don't. Okay. So otherwise, I'm going to just continue on what we were doing last time. So one thing is, yeah, sorry again last time for going so fast. The thing is, I realized that, okay, I have all these TA sessions planned with the questions. So I really want to have enough material for each, for you to be able to have at least 1 week to do it. So that's why we went fast. Okay, so today we're going to do the end of chapter 4. So we had finished. By the way, I haven't heard from anybody. The sound is working fine. You hear me well?
Yes, sir.
Okay, good. Now I feel reassured. All right, so we had seen associative law of matrix multiplication. I'm not going to, yeah, I might ask for a proof in an exam, I don't know. Or thing is, it's no, probably not, because it's tedious to do, but it can be done. Yeah, so I've seen all the laws of matrix operations. All right, so yeah, so let's go with special matrices. So one is the neutral element. So what are neutral elements? So in arithmetics, we have, oh yeah, let me monitor the discussion too. Good. So we have a neutral element of addition. Which is, somebody can guess? it's 0. Why? Because if you have 3 plus 0 equals 3. So that's why. And we have the neutral element of multiplication, which is what?
1.
1. Yes, because if I have 3 times 1 equals 3. So we have the same thing in the matrix algebra. So we have the neutral element of addition for matrix algebra. So the neutral element of addition is the 0 matrix. So you may guess what it is. It's a matrix of zeros. So if I have something like this, so A, B, C, D, and then the 0 matrix is just going to be 0, 0, 0, 0. Then it's going to be equal to, well, it's A plus 0 equals 0, B plus 0 equals 0, C and D. So 0 matrix is the neutral element of addition. Then the neutral, copy that, neutral element of multiplication. Somebody knows?
The identity.
Yes, identity matrix, which we note I, and which is a matrix that has, well, it's a diagonal matrix with only ones on the diagonals and 0 everywhere else. So let me show you an example. So if I have any matrix, like for instance, this one, so A, B, C, F times the identity matrix. So this is the identity matrix. So 1, 1, and then zeros for all the rest. So let me just compute the first element. So first of all, question for you. I know it's early in the morning, but how big is going to be my final matrix? Oh yeah, no, that's bad. Yeah, it's early in the morning. Man, so yeah, this is wrong. Yes, this is better. So what's the size of the resulting matrix there?
3 by 3.
3 by 3. So why 3 rows?
I'm actually not sure. It is early.
Yes, but thank you for going along. It's perfect. Oh yeah, somebody said, yeah, 2 by 3. So one thing you may guess is if I'm telling you it's a neutral element, so probably it means that when I multiply it with some matrix, it doesn't change. So yes, I have 2 rows here, or 1 row 2. So it's going to be a 2-row matrix, and then for the number of columns is the second matrix I'm looking at. So it has 3 columns. So it's going to be a 2 by 3. And yeah, so let's just do the first element there. So I have A times 1 plus B times 0 plus C times 0. So that's A. Then second element, I have second element here. I have A times 0 plus B times 1 plus C times 0. So that's B. And third element here, I have A times 0 plus B times 0 plus C times 1. So I have C. This element, D times 1 plus E times 0, F times 0. So that's D. And you see I get E and F. So nothing changed. And also I could have, so that's if I post multiply by the identity matrix. But if I wanted to pre-multiply by the identity matrix, so what kind of matrix would I need? Here, what size? What do I need? What do I need for my first matrix for me to be able to multiply with the second matrix? Oh, Patrick said yes, 2 by 2, perfect. And Aidan, yes. So I need 1, 0, 0. So the identity matrix is any matrix size which allows me to do the operation I like, either multiply or divide. So why would I use it? Well, usually, yeah, it may looks like, oh yeah, why do I need that? Well, you'll see later why you need that. But as a first guess, you might say, well, maybe I want to multiply everything by a scalar. So I put some scalar B here, for instance. So it's, or no, well, B is there, so some other scalar, for instance, but that would be a way to do it. And then what do I get? Sorry. Yeah, so I get two rows and 3 final columns. And you can see that first row is 1, 0 times AD, so it's A. Then B, C, D, F. So that's the neutral element of, yeah, and of course, so crucial point. So the number of elements, the dimensions. So that's true for, of course, the 0 matrix. So it has, if you're adding to my 2 by 2 matrix with the 0 matrix, then it has to be a 2 by 2. The same with the identity. It has to, of course, it's a square matrix. So I'm just going to say square. Dia. Ones. All right, so I've already talked about the idempotent matrix. Somebody remembers the idempotent, what it does? Ah, yeah, good. A equals A. All right, some idiosyncrasies of matrix algebra. So yeah, so usually in the arithmetic, we have intuitions about things. So for instance, if you have a times x equals 0, so you assume that either a is 0 or x is 0. But that's not necessarily the case for matrix algebra. So I'll give you an example. So for instance, if you have so 2, 4, 1, 2, which multiplies minus 2, 4, 1, minus 2. See what I did there? I just put negative elements there, and magically, what I'm going to get is, so let's do the first one. Yeah, 2 times minus 2 is minus 4. Plus 4 times 1 is 4, so I get 0 here. 2 times 4 is 8. 4 times minus 2 is minus 8, so I get 0 here. 1 times minus 2 minus 2, plus 2 times 1 is 2, so minus 2 plus 2 is 0, and then I get 0 again. So that's very strange, no? Very surprising. Yeah, so that's one surprising thing about the matrix algebra is sometimes you can get things to cancel out and get you a zero matrix, even though you didn't, yeah, no zero is involved anywhere here. One other thing that you have to be aware of, so in arithmetic, if you have, say, ax equals bx, then you can be pretty sure that you can just divide by x on both sides and you get a equals b. If x is not 0, of course. But in matrix algebra, not necessary. So somebody has an example where this is not the case for matrix algebra. It's somewhere on this page there.
I mean, technically, if x equals 0, then both of them, when multiplied, would equal 0. But if they're the same, it would still work. Like a could still equal b. They could still be 1 times 0 plus equals 1 times 0.
not sure I understood. So what I'm saying is, can you give me an example in which AB equals, let's say, AC, and then this does not imply B equals C. No idea, too early in the morning. So it's just the two last examples we've seen. So here's one. So this times the zero matrix equals the zero matrix, because I just multiply everything by zero, and I see that this equals this as well. But of course, 0, 0, 0, 0 is not equal to -2, 4, 1, -2. So that's a case where you just multiply by a different matrix and you get the same result. Or one other case is the idempotent matrix. So AA equals to A, but you get A times the identity matrix will equal to A as well. But A is, of course, not equal to the identity matrix necessarily. So so that's very strange and counterintuitive sometimes. Okay. So other sort of matrices. Symmetric matrices. So it's when A prime equals A. So for instance, so 1, 2, 2, 4. Equals to 1, 2, 2, 4 prime. That's pretty straightforward. So how do I see it? Well, I just invert every element. So I look at the element ij becomes the element ji and vice versa. And if they are all the same, then of course it means that the matrix is symmetric. And of course the diagonal elements do not change. So, and of course, only square matrices. Maybe symmetric. And finally, a super important matrix. So question about the inverse symmetric matrices. All good? All right, last but not least, very important matrix, inverse summer matrix. So as I've said before, so in matrix algebra, division is not defined. But what we can do is multiply by the inverse. So what is an inverse matrix? So inverse matrix. Given a matrix n by n has to be squared. It's just given an n by n matrix A. Its inverse is A minus 1, such that A times A minus 1 equals A minus 1A equals the identity matrix. But not all matrices have, and that's, I'm going to note it n here to see that it's a n by n identity matrix. Yeah, note. Not all matrices, not all square have inverse. I'm going to give you the formula for a 2 by 2 matrix. So for example, for a 2 by 2 matrix, if A equals A, B, C, D, then A minus 1 equals to 1 over AD minus BC. Oops. Which multiplies D minus B minus C A. And if I compute it, then A times A minus 1 equals ABCD times this. Okay, so let's do the first element. AD minus BC, yeah. Sorry. So you see A times D and B times minus C, so AD minus BC, divided, of course, by AD minus BC. Second element, A minus B, and then second it's D, BA, sorry. So minus BA plus BA, so divided by AD minus BC. Third element, CD minus CD. divided by AD minus BC. Then fourth element, A minus B times DA. So, oh no, sorry, C minus B, yeah. Minus BC. Plus AD divided by AD minus BC. And that is, of course, equal to so this is AD minus BC divided by AD minus BC, that's 1. AD minus BC divided by AD minus BC, that's 1. And then minus AB plus AB, that's 0. And CD minus CD is 0. So we get this element. So is that black magic? No, it's just math. There's a way to find the inverse of every matrix, which we'll see later on. So, and one important note. Okay. Let's put some asterisk there. So AD minus BC is called, somebody knows the name? No? It's called the determinant of the matrix A. And this is a super important concept. And note the following. So A minus 1 equals to 1 over the determinant times this matrix there. So what if AD minus BC equals 0? Can I do something now?
Well, everything would become undefined. Everything would be divided by 0.
Yes. So note, if the determinant is 0, then the inverse is undefined. A minus 1 does not exist. So that's a neat trick. If I know how to compute the determinant of a matrix, then I can already say, okay, that matrix has an inverse, that matrix doesn't have an inverse. So and what we're going to see is actually that every time the determinant is non-zero, then the inverse does exist. And yeah, so otherwise it does. Does exist. And what's the link with what we've seen so far? So solving systems of equations. Well, it turns out that having an inverse for the matrix ABCD, if ABCD are the coefficients of the system of equation that I care about. So if I have, say, 2 equations with 2 unknowns, and these are the coefficients, then if I have an inverse, I know that my system has a unique solution. If I don't have an inverse, meaning if the determinant is 0, then in that case, I will know exactly right away that there's no way for me to solve it. So I don't have to go ahead and try and solve everything. The determinant is just a neat way to do it right away, very fast. Okay, so one thing that I said here is a minus 1 equals a minus 1a equals in. So how do I know that? How do I know that the a times its inverse is equal in, and its inverse times a is equal? So it could have been possible that a times its inverse equals in, but then its inverse time a minus 1 minus 1 equals in. In other words, how do I know that a minus 1 equals a? I don't know. I've done some research, and yeah, it's not written in the book. And yeah, so there's obviously there's a reason why. So what it means basically is that the inverse is unique. So I could just write a minus 1. So it implies that the inverse is unique, but this so if somebody knows proof about this, then you can tell me. Yeah. But so we have to assume that this is the case. So I like to assume nothing, but here really I was trying to find the proof of this, and I couldn't find it. So
excuse me, Professor.
Yeah.
Could you please repeat the part where you said that the inverse is used to find whether the problem has one solution? I'm not sure I got that right.
Okay, so therefore, imagine I have following equation. So I have ax plus py equals k, and have cx plus ty m, for instance, I don't know. Then this system can be written as here I'm going to have A, B, C, D. Which multiplies my two variables, x and y. And here equals my this system as unique solution if the determinant of ABCD, which is AD minus BC. Oops. Yeah, I should change this shortcut. Is non-zero. So every time you have a system of two equations, two unknown, then you just compute AD time minus BC, and you know if you have a unique solution or not. Don't have to solve anything. Of course, at some point, solving is quite easy if you have only two variables and two equations, but still it's a neat simple trick to know. Of course, I'm going to tell you much more about what the determinant is, where it comes from, how we compute it, and the inverse as well. So this is just to show you where we are. All we care about always are finding solutions to this these sorts of systems. Okay, so
Thank you.
No problem. So some properties. One, so only square matrices have inverse. But not all of them. So in other words, being square is necessary, but not sufficient. Two, a matrix that has an inverse is called non-singular. And you can guess a matrix that does not have an inverse is called singular. Yeah, now that I'm thinking about it, I don't know where the word singular or non-singular came from. Somebody knows? Singular, non-singular. It's kind of strange because you imagine a non-singular matrix gives me a singular solution for the system of equations. But somehow, if you don't have a solution, then it's singular. We thought that maybe because the matrix has only one form without the determinant. As a non-singular matrix also carries the determinant. Not sure if I'm following here. Yeah. Okay. Okay. So yes, since the inverse is there's a single inverse for a matrix which has an inverse. Yeah, maybe. Anyways, I don't want to lose time on that. That's how mathematicians decide it was named. So when you hear, so in econometrics, you're going to hear that a lot. So is something singular or non-singular? This means can you find a model which has a neat solution, or don't worry, it's difficult for everybody in the morning. Yeah, so in econometrics, you might hear this. So is your system non-singular or singular? Singular means bad and non-singular means good. That's how you have to remember. If something is singular, it's not good. You don't want to have to deal with that. Okay, so proof that each inverse is unique. So this is going to use this property right here, that a minus 1 equals a minus 1a. But the thing is, yeah, so I'm just showing you the proof that they show in the book, but I'm not satisfied because who knows that a minus 1 equals a minus 1a? So they don't say it exactly. Maybe there's an obvious reason, but I haven't seen it yet. But anyways, that's what I'm going to use. So assume that B and C are inverses of A, and that they may or may not be the same matrix, who knows? Then AB equals what? So you do it with me. If B is an inverse of A, then A times B equals oh, it's hard. If B is an inverse of A, then okay, A times A minus 1 equals what?
It'll give us an identity matrix.
Yes, thank you, identity matrix. So now let's pre-multiply by C on both sides. So I get C, which pre-multiplies AB, equals C, which pre-multiplies I. Since AB equals I, I'm allowed to do that. And then what I'm allowed to do is use the associativity of multiplication and write CA minus B equals CI. And this I'm using associativity of multiplication. And then what is CA equal to?
C. Or oh, sorry, I as well.
Yes, exactly. So I get that I times B equals C times I. And then this you can just write by assumption. C is an inverse. And then of course I get that B equals C. So if that doesn't look too convincing to you, it's normal. Well, the thing is, so we have to use this property that A minus 1 equals A minus 1. So yeah, maybe I find at some point where that comes from, how you prove that. But if you use this, then this is super trivial to show. You just have to pre-multiply by C on both sides and you find that B equals C. So B is the same, so B and C are the same matrix. So yeah, so the inverse is unique. So why am I showing you this? So I'm showing you the sort of thing I would like you to do when I ask you to prove something. So obviously you're going to, if I ask you to prove this statement, you're going to look at it and say, how should I do that? I'm not sure. What you should have in your mind is some ideas. Oh, let's try this. Let's try that. Oh, that doesn't work. Oh, that works. And then you sort of make your way to the solution, to what I want you to prove. And step by step, it's nice if you say, oh, I'm allowed to do this step because I'm here applying some property I know. So here, for instance, C times AB, I know that it's equal to CA times B because of associativity of multiplication. Yeah, matrix multiplication, I can write, which we have seen in class. Now, I'm not a mathematician. It's a mathematical A minus. I come from A times I can be transformed in I times A minus 1. Yeah. So thanks, Patrick. I'll think about it. I keep, yeah. Anyways, I don't want to think on my feet right now because we have many things to see today. Yeah. So so what I was saying is I'm not going to be super strict. I'm going to give you partial credit for partial steps, and I'm not, yeah. So I couldn't even do a perfect proof that would satisfy a mathematician. So, but I still want you to more or less start feeling what it means to prove something in mathematics. So it's going to be not too difficult proof, hopefully. And yeah, what you can do is every time we have seen something in class, then you can say, oh, I'm using this property. If here, what property are you using to convert CA into I? Well, that's just something that we have assumed here. We have assumed that C is an inverse of A, so C times A is equal to I by the property of inverse. So this kind of things. So other properties of inverse. Yeah, this I've said. A minus 1 minus 1. So A inverse equals A. That's the whole point. Then inverse of multiplication. So of product. So if I take AB, this is super useful, minus 1. It's like the inverse of transpose. Somebody remembers what inverse of transpose is? If I have AB transpose, what that was equal to?
Was it just BA?
Yeah, but something is missing. It was B transpose, A transpose. And here it's the same thing. So AB transpose is AB minus 1 is A minus 1, B minus 1. But I changed the order of multiplication. Of course, if B minus 1 and A minus 1 exist. If they don't exist, if they're not square matrices, then their product may have an inverse, but they themselves may not have an inverse. This is going to be very useful. Now, last useful property, inverse of transpose of inverse, A minus 1 transpose equals to A transpose minus 1. So all of these things, I could give an example or try and prove them, but yeah, we don't have time. So that's so I'm just giving you these properties that are very useful to in the future, to use in the future. Now in the book, we have geometric interpretations. Yeah, in the Chang. You have geometric interpretation of a vector operation. So that's super interesting. If you want to dig deeper into this, go ahead. I had prepared a whole class almost on it, but I realized no time. So do on your own for fun. Not going to ask anything about it in the exam, but that's a very neat chapter. Yeah. So there was actually something about linear independence, but we've seen it. Yeah, vector spaces, all of these things. So it's quite nice. Concept of distance, but no time. Okay, so that's it for chapter 4. Questions about what we've seen so far. So these things, yeah, I could spend more time trying to show them, show examples, show properties, but yeah, let's take them as given right away. You have to learn them because this is true. Okay, we're good. So if we're good, then let's go ahead and continue. So chapter 5, which I have titled what? Solutions to linear system of equation. Yeah, this is going to be a section. So now we're going to see what this is more precisely, what the determinant is, how you find the inverse of matrices, all these good things. All right, recall a linear system of equation has a unique solution if all equations are independent of each other. So, for example, suppose we have the following system. So x1 plus 2, x2 equals 1, and have 2x1 plus 4x2 equals 2. So is there a solution for this?
No, because they're the same, just multiplied by 2 for the second one.
Yes, exactly. No solution. Second equation. Is the first multiplied by 2. And note, by the way, that if you remember the determinant, here it would be 1 times 4 is 4 minus 2 times 2, so 4 minus 4. So the determinant would be 0. So we already see visually that we cannot have a solution for that, since we know what the determinant is. So here, how many solutions would I have for x1 and x2?
None.
None?
No, infinity.
Yes.
Infinite.
We would have infinite solution. Because in the end, what I can get is if I divide the second one by by 2, I get x1 plus 2x2 equals 1. So in the end, I have only one equation. It looks, I made you think that I was generous and giving you a nice system of 2 equations and 2 unknown, but in the end, it's not the case. I was just giving you one. And this means that any combination of x2 and x1, so for instance, if I have x1 equals to 1 minus 2x2 for any value of x2 and x1 that's compatible, then this works. But if I give you this one, so instead of this, I give you 4, for instance. So then how many solutions? We just said it seconds ago.
It will have infinitely many solutions too.
Are you sure?
Yeah.
It'll have no solutions
Oh,
because
sorry,
they're
yeah,
not the
that's why I
exact.
didn't see
Yeah.
the 4.
Yes, no
You're right.
solution. So in one case, so it's the same set of coefficients. In one case, you get infinitely many. In the other case, you get no solution. So yeah, I would, okay, let me show you graphically what this means. So yeah, so I get that. So let's use the first one. So yeah, let's just try it very quickly. So, okay, so we have x1 plus 2x2 equals 1. So which point can I use? So if I have x1 here, x2 there. Yeah, so if x1 equals 0, then x2 equals 1/2. So 1 point there. So let's say this is 1, so 1/2 would be there. And if x2 equals 0, then x1 equals 1, so that would be there. So that's one equation. And then the other, instead of 1, I get 4, so, or I get 2, right? So I would get something like this. Just to be sure, I'm going to compute it in my head. Oops. So if I have x1 equals 0, I get x2 equals 1. That's it. Yeah. So what are the set of points that are compatible with these two equations? Well, none. They're parallel. They're going to go forever in each direction. So no solution. In the other case, when this was 2, so we had the same equation, and in that case, we had just exactly the same equation. So in that case, we had an infinite number of solutions. So what we want essentially is to have different set of coefficients. So we don't want to have the coefficients being just the same set of coefficients multiplied by a scalar. All right. So this is true for a two equation system, but it's going to be true for a higher number of equations as well. So let me go back to my, yeah, I can even, let me, okay, yeah. Okay, so the problem arises when when the coefficients of one equation are are multiples of the coefficients of another equation. So if I put it in matrix form, so in matrix form, if I have a 2 by 2 matrix, then I would have, for instance, A1, oops, A1, A2, A1, B2 times XY equals A3, B3. And note that, so this is if if B1 and B2 are just a multiple of A1 and A2, then I'm in trouble. I don't have a unique solution, but then if whether I have an infinite number of solutions or no solution, it will depend on A3 and B3. But it doesn't really matter. What we want is to have a nice single solution for our set of equations. So how can I say that? So it would be a problem if, for instance, B1 was A1 multiplied by some number and B2 was A2 multiplied by the same number. So yeah, problem if B1 equals to say lambda A1 and B2 equals to lambda A2. Oops. Right? So that's what we don't want. And then we can find the solution that lambda would have. That would mean, so let's divide one by the other. So I get that B1 divided by B2 equals, whoops, equals to lambda A1 divided by lambda A2. And so I can get rid of the lambda there. I really don't really want, I don't really care about it. And here I can just multiply by A2 here and B2 here. And here I can, yeah, let's put all of that on one side. So if this is equal to 0. And what is this? Oh, let's put it here like this, so it's very clear. A2, A1, B2 minus B1, A2. What is this thing?
Is it the determinant?
Yes, exactly. So that's, we're finding out exactly what we were saying before. So the problem is if this vector is not linearly independent from this vector, meaning if I can just multiply this vector by some constant. And how does that concretely manifest itself? Well, if that is the case, then I'm going to find that A1, B2 minus B1, A2, the determinant is 0. That's exactly what we were saying. So in that case, the determinant is 0. And so the label, let's put this in bold because it's important. So we label the determinant yeah, if I have a matrix there, so it's just going to be yeah, this. So it's like in absolute values. You put it between vertical bars like this. So this means determinant. Okay, so let's go and just describe some properties of the determinant for 2 by 2. So some properties. Oh, yeah, it's 10 already. So yeah, why don't we take a small break and continue after that? So let's take 12 minutes maybe. So come back to at 10, let's say 10:14. Okay, welcome back. So yeah, I was about to talk about some properties of 2x2 determinant. So these properties scale for higher orders, but I think you'll be happy that we just look at them in 2x2 matrices. That's enough, and trust me, they work in higher orders. But yeah, we don't have time to prove everything. So first properties, we can flip rows and columns. So what this means is the determinant of A. How do I write this? Too many math characters. Equals the determinant of A prime, of A transpose. So it's quite obvious. So if I have the determinant of this is A1 B2 minus B1 A2, and the determinant of if I flip these two, well, of course, it's going to give the same thing. I get A1 B2 minus A 2B1. Or right, it's just that the order of operation for a scalar multiplication doesn't matter. Also, so we can add a row multiplied by a constant to another row. Without changing the determinant. So this, think about it, it's like if I have a system of two linear equations, imagine that they are fine. So I have, so imagine I have 3 here instead of a 4. I'm going to put back the 4, don't worry. And then I said, oh, let's take this equation and add this to that one and have this system instead. Well, it doesn't change the system by itself. Since there's a unique solution that fits this and this. So if I just add one equation to the other, then it's still the same system of equation. So this is going to be reflected in the determinant as well. So for instance, if I have this, but let's add to the second row the first row multiplied by some constants. So plus sigma A1 plus sigma A2. Then the determinant of this would be A1 times B2 plus 1 minus A2 times B1 plus sigma A1. So if I just do these operations there, so you see what's going to happen. I'm going to get A1 times times A2 sigma here, and A2 times A1 sigma there with a minus sign. So what's going to happen? They're going to disappear. So I can just multiply these. And these cross terms, A1, A2 sigma, cancel each other. So this is going to be equal to the determinant of this matrix there. Other property. A row, multiplying a row by a constant. What does that do? If I multiply one row by a constant, think about it. Try your luck. It's like that equation with the infinite solution. Not exactly. So imagine if I multiply A1 and A2 by some constant, think about what's going to happen to the determinant.
The determinant is going to be changed by the same constant. So
Yes,
you multiply
exactly.
the constant with the determinant.
Yes, perfect. That constant. So let's do that. So let's have some constant, new constant mu equals mu A1 B2 minus mu A2 B1. So this is going to be equal to mu times A1. So it's going to be equal to mu times the determinant of A1, A2, B1, B2. Yeah. So should we care about that? Well, it's funny because if you think about, oh, I just add a constant times this, and oh, it doesn't change the determinant, but then I multiply a row and then it changes the determinant. It's counterintuitive, and I wouldn't have expected this property to be the case, but that's the case. But so does that change how we use the determinant? Well, not exactly, because what we care about, well, of course, by a non-zero constant. Because, well, actually, no, it works even if it's zero. Yeah. But what what I was about to say is what we care about is the determinant zero or not? That's really what causes problems for us. So if you just multiply a row and it multiplies the determinant by some constant, but who cares if the question is the determinant zero or non-zero? Then trickier still. So inverting 2 rows or 2 columns. What does that do?
You multiply the determinant by -1.
Yeah, good. Awesome. I this too, when I saw that first, I was like, really? But yeah, it is. By -1. So let's go ahead and do that. Oops. So instead, we're going to have P1, 1, P2, A2 equals 2, P1, A2 minus A1, B2. And it's going to be equal to minus here, this becomes plus, so I'm going to put it in front. So it's just minus times the determinant of this matrix. That's a funny property too. And then again, but multiply by -1 doesn't really matter. So, but that's funny. It's like if I give you the equation in one order or the other order, it's the same system, but somehow it changes the determinant. All right. Oh yeah, and finally, so for graphic interpretation of the determinant, I highly recommend. This thing there. Let me try. This video there. Well, all his videos are awesome. If you like mathematics, I would say it's 3 blue, 1 brown. So yeah, it's the best, probably the best channel for mathematics online to learn and to just enjoy. So some channels are like, oh, they're going to explain to you how you compute a determinant or how do you do that in a very technical and scholarly way. And some other channels on math, they're just going to entertain you, but not really in a super useful way. But this guy is Grant Sanderson. So I'm not sure. How do you spell that? Yeah, Grant Sanderson. So he has a whole series on linear algebra. So all of this, he always uses 2x2 matrices and uses a lot of graphical interpretation. So it's super good to understand what's going on. Really, if you want extra insight, I highly recommend it. All right, and then you don't have to come to class; you just listen to his thing instead. Okay, I'm just kidding. Class is good too. In R3. So what's going on in R3? So here, this is just everything we've done so far is in R2. So R means the real, but with 2 dimensions. So 2 equations and 2 unknown. But we could look at 3 equations, 3 unknown, 4 equations, 4 unknown, etc. But it's more and more difficult to visualize what's going on. So what's going on in R3? So a set described by one equation. Well, I could say that just to show where we're coming from. So in R2, a set equation described by one equation is what is it? One linear equation. Yeah, linear system. So if I have only one equation, what do I have? It's right there. If I imagine I only have this equation there, what does that describe? Oh, yeah, I'll paste the link in the chat.
A line.
Yes. So don't look at it right away. Wait a bit. Is a straight line. And a set described by 2 equations, 2 linearly independent. Is what is it?
It's a point.
Yes, it's a point. It's a unique solution as we want. That's what we care about. Now, this is in R2. In R3, a set described by one equation is, this is, you have to know that or guess.
I'm not sure, but I'll guess a 3-dimensional space.
Yes, in 3-dimensional plane. Yes, a plane. So if I have, for instance, so the set is 3 points, X, Y, and Z. We write this in math better, such that I can't type anymore. Where is my? Oh yeah, okay, here it is. Such that A1 X1 plus A2 X2 plus A3 X3 equals A4. So how do I know this is a plane? Well, imagine the following. Imagine that A3 equals to 0, okay? So I only have A1 X1 plus A2 X2. What is this? A1 X1 plus A2 X2 equals A4. It's a straight line. It's like this line there. But now I have a 3rd dimension. So what does that mean to have a 3rd dimension? Here I would have, for instance, X and Y, and then I would add a Z dimension there. And I haven't said anything about Z. So essentially for any value of Z, since I have a coefficient 0 here, since A3 would be 0, I could have any value of Z. Oh, what am I writing there? Sorry, X, Y, and Z. Yeah. So for any value of Z, my equation would work because I have 0 there. So I have Z equals 2 or -4 or plus 1 million. Who cares? There's a 0 in front. And what would that look like? It would look like I have a third dimension there going in the, it's very hard to see if I'm not in front of you, but imagine that there's a straight arrow going inside my computer there. And so this would be a plane essentially. And if I have I add some other constraint on Z, then it's a two-dimensional plane in 3 dimensions. I'll show you a drawing. You're going to see it right away. And now, if I have a set described by 2 equations, what is it? So you have to guess again.
It'll be a line.
Yes. And so if I have a second equation, so I have, say, P plus P2 plus P3 equals B4. This is a line. So here I have 2. So you see that the more equations I have, the more constraints I have. A plane means I can have a lot of leeway in choosing X, Y, and Z, anything that fits in the plane. Here, if I have 2 planes, by 2 linearly independent equations, then they're going to intersect at some point, and this intersection is actually just a straight line. And then if I have a set of described by 3 linearly independent equation is what is it? A point, yes. So if I have, let me more strict. This, and third equation. Because I have 3 equations and 3 unknown, so I can have only one solution that is compatible with the 3 of them if they are the 3 of them are linearly independent. And then I'm going to, so I can write it in or in matrix form. I would have 3 by 3 matrix, A1, A3, P1, P2, P3, C1, C2, C3 times X, Y, Z equal to, what is it? Yeah, A4, B4, and C4. And yeah, do I still have my picture? Yeah, I have it. It's nice. So I cannot draw, but I found some artist on the internet that was very good at drawing a nice shape. Okay, nice. Here it is. So you see what's going on. You have one equation, it describes a plane, for that one, for instance. Then two equations describe two planes, but I want a solution that's compatible with the two of them. So it's only the intersection of these two planes which is going to describe a line. And then if I had a third condition, a third equation, then that red one, for instance, then it would intersect the two others, and there's only a single point that would be compatible with the three equations at the same time. All right. So I couldn't have drawn that, not good enough. And then,
So
yeah, go ahead.
So if even just two planes are the same, like as in if let's say if b1x plus b2y plus b3z equals b4, and the one after that, c1x plus c2y plus c32 equals c4, if it's the same thing just scaled up, there'll be an infinity of solutions, even though it's just two, the first one's different.
Yes,
Okay.
exactly. And more than that, if you can find, for instance, a way in which the third row, the third equation, can be found by combining the coefficients of the two the first ones, then again it means that you don't really have three equations, you only have two. They're not linearly independent. So that's why this last bit that I added at the end of the last class, what does that mean to have three vectors that are linearly independent is you cannot recover a third vector from the two first ones, or a nth vector from a linear combination of the n-1 previous ones. So it's the crucial point about it. That's what it means to have a linear independence. Otherwise, you're going to just get a line, or you're going, even if the three are the same, then you get just the same plane, and you can get as many solutions as you like. And what does that mean, actually? So what would it mean if they are not linearly independent? So you would get something like this. So if so you have some combination, if gamma 1, if gamma and say u exist such that you can combine first and second and get the third one. So for instance, C1 equals to gamma A1 plus U V1. And then the second one the same, C2 equals gamma A2 plus U B2, and third the same. So this is what we mean by linearly dependent. So the third equation would have coefficients that would be linearly dependent on the first two. And well, I'm just telling you that. So what I could give, what you could do is just start with a system with A1 and A2 and A3, B1, B2, B3, C1, C2, C3, and see that if this happens, then you get something weird. You get a case in which you have infinite solution or no solution the same way. But yeah, we don't have time to just do that all over again because it's a tedious computation. But this is essentially what you would get. And then I could do the same as before, as I did with my first case. So I could, for instance, finding mu, then gamma, using the 3 equation. So it's a bit tedious. Should I do that or should I not do that? Do you trust me or do you not trust me? Let me just show what you could do. So for instance, yeah, you start, you want a solution for gamma, so you find that gamma A1 equals to C1 minus UB1. So I just added UB1 on both sides, and then you find that gamma equals this. Then you substitute gamma in second and third equations, and so on and so forth. So you just solve, and then you can get rid of gamma and mu. And I'm just going to show you in the end what you get. So when the smoke clears, so what you get is the following. 0 equals, yeah, it's a bit tedious. Yeah, you can do it on your own. And you find the following. So A1 times C3 B2 minus B3 C2 minus A2 times P1 C3 plus, oh, is that plus? No, I think there's, yeah, no, it's a minus there. Minus B3 C1 plus A3 times C2 B1 minus B2 C1. So just to tell you what I was doing, so I just found this for a 2x2 matrix. If you can express B1 equals lambda A1, B2 equals lambda A2, so you find that this equals 0. So this is the determinant for a 2x2 matrix. And if it equals 0, then we know we're in trouble. So now I only did exactly the same for a 3x3 matrix. It's just, it can be done. It's just tedious. And this is the final solution that you get. So A1 times C3B2 minus B3C2 minus A2 times B1C3 minus B3C1 plus A3 times C2B1 minus B2C1. And does that look like something to you, these things? C3B2 minus B3C2, does that look like something?
Like the determinant?
Yes, it looks like a determinant of what? a two by two matrix. So that would be B2, C3, and B3, C2. And that would be a determinant. Oops. And that would be a determinant as well. So here is B1, B3, C1, C3. And here is B1, B2, C1, C2. So this is the determinant of a 3 by 3 matrix. And what is it exactly? So let's look at it. We have A1, so the first element on the left, top left, times B2, the determinant of B2, B3, C2, C3. So here, let's look at this. You have the A1 times the determinant of this submatrix there. Then we have minus A2 times the determinant of this submatrix there, B1, B3, C1, C3. And then plus A3 times the determinant of this submatrix there, B1, B2, C1, C2. So this is going to be the way you find any determinant. It's very neatly defined recursively. So it's you just pick a line. It can be any row or any column. And if I start with the first row, for instance, it's the first element times the determinant of the remaining matrix times the second minus the second element times the determinant of this remaining matrix and plus this third element times the determinant of this. And if it was a 4 by 4, so it would be again the same thing. You pick a row or you pick a column and you do this, you alternate the signs, minus, plus, and you compute the determinant of the remaining matrices each time. And you can imagine that if you have a 4 by 4 or a 5 by 5, it just becomes extremely, extremely long to compute determinants. So this is why for very large systems of say thousands of equations, then we can compute exact determinants numerically, but it takes so long, so many operations that there's a big science that targets finding numerical values, numerical approximations of systems instead of exact systems or exact solutions or exact determinants, because they're too long to compute. So you see already I had two terms for a 2 by 2. Now I have 1, 2, 3, 4, 5, 6. And if I have 4 by 4, can you imagine how many terms I would have? I would have four rows multiplied by the number of terms in each 3 by 3 determinant, so 3 by 2. So for a n by n matrix, the determinant has n factorial terms. So it can be quite long to compute. So that's why a factorial is good, because it's exclam at the same point. You have many terms. All right. So now I just told you more or less intuitively what this is. Now let's just be a bit more precise. So this is the determinant of 3. Okay, determinants. So these are general properties of determinants. So the determinant of a square matrix A is written so either A like this or det A. For a 1x1 matrix, wouldn't it just be easier to reduce 2 1x1 matrices using the same strategy? You mean, thing is, I don't lose terms, right? Let me maybe interpret what you were thinking about. Is what if I just reduce this for some reason and continue from there? Thing is, here
Yeah,
go ahead.
I was saying like it's 3 by 3. It's A1 times the determinant of B2, B3, C2, C3 minus A2 times that matrix plus A3 times the
Yeah.
last one.
Yeah.
But then if we take those submatrices and apply that same strategy, if we had like a 10 by 10 matrix, that would be much simpler than
No,
just doing it once and solving.
Yeah, so I think what I see what you're saying. So you're saying essentially, if I have a 10 by 10 matrix, if I do the underlying work, it makes my life easier later. But here's why it's not the case. Because here, for instance, I use A1 times this determinant, but this doesn't help me at all with the rest. Because then it's A2 with this determinant there. So B2, C2, here the first one is B2, C3 times minus B3, C2. Then it's B1, C3 minus C1, B3. So these are completely different operations. So but I see your intuition there. But yeah, it's just painful. We're just stuck.
You'd be adding like 100 terms for a 10 by 10 matrix if you did it.
Yeah, 100 by 100 means 100 factorial. So 100 factorial is
no, I'm saying for 10 by 10.
So 100 factorial is this many terms. So that you just get out of hand super quickly. Yeah, we're in 100 in a bad spot. All right, but don't worry, in the exam, I won't go higher than 16 by 16. No, I'm just kidding. So 2 by 2, maybe I'll see. I'll do something that's doable. So yeah, for a 1 by 1 matrix, the determinant. Let's say that the matrix is A, for instance. which is just a scalar, then the determinant is simply A. So a 1-by-1 matrix, if there's a single element, then the matrix is that element, that's it. And for n by n matrix, we compute. Well, there are many ways to compute the determinant, but I'm telling you the more traditional, intuitive way. Using the Laplace transform, which is this. Sorry, not transform, expansion. For the famous physicist / mathematician in France, Laplace. So this is going to be like just cooking. So it's, you have to follow the rule, and there's no big insight behind it. Just learn how you do it, and that's it for a matrix. IN, the determinant equals this thing. So it's sum I equals 1 to n of -1 I plus j. I'm going to explain all these things now. Just write them down or let them sink in. Aij times the determinant of matrix Aij, which I'm going to explain what this is, so don't panic. And it's also equal to, so here I used a row to do it. No, a column, I think. Yeah, if I is a column. Did I? Anyways, I can use a row or a column, and then j 1 to n -1 and yeah, the rest is the same. Where ij equals 1 to n, and so so what is Aij? It's a shorthand for what we were saying here. So it would be here, this, for instance. Aij is called a minor of A because it's a minor matrix. And is the determinant of the matrix A without, so this is important, without the row I and column J. And the -1 I the I plus j is called a cofactor of A. Sorry, -1 times the minor. Yeah, I'm not saying anything. So that's what students often ask. Can you swear that we're not going to have this at the exam? No, I'd rather not. What I'm going to tell you is it's going to be feasible. So, but yeah, so I don't know exactly what's going to be in the exam yet. Because if I just give you 2 by 2, then you just learn the formula. You just learn this formula and you're good. A1, B2 minus B1, A2. Oh, I don't need to learn anything else. Yes, exactly. So at some point, it's just a bunch of 2 by 2 determinants. So of course, I am totally aware that in the exams, everybody makes a mistake. So you can mess up, you can pick the wrong row or number or whatever. So so you have to be careful and check your computation. But yeah. So it's possible that I give you more. And I'm going to tell you actually why it's possible that I can give you more and that it's not too difficult. So let's go with an example. So example. If I have, let's say a 3 by 3. One, 2, 3, 4, 5, 6, 7, 8, 9. So
just to make sure, when we're saying that determinant is equal to the sums, that second equal, should that be a plus or are they interchangeable?
Yeah, it's an equal. Yeah, it's
Okay.
here. I'm just saying. So if I is the column, then I could go with so column 1 and then column 2 and then column 3. So this times the determinant of this times this determinant and this, or I could go with one column and go with rows. For instance, 1 times this determinant, then 4 times this determinant, then 7 times this determinant. It always gives me the same thing. It's just saying, yeah, I pick a row and go column by column, or I pick a column and go row by row. So now let's go with this, for instance. So let's go with 2, 5, and 8. So I get what? So first of all, what is my multiple in front? -1 to the 1, because it's row 1, plus column 3. So it's 1 plus 3. So this 1 plus, sorry, it's column 2. So 1 plus 2 is 3. So -1 to the 3 is -1. So here I get them -1. So to know what the sign of this are going to be for a 3 by 3 matrix, it would be something like this. So I get 1, -1, 1, -1, 1, -1, 1, -1, 1. So it's just, yeah, it interchanges. And it's neatly expressed by this. So it's -1 exponent I plus j. You can imagine if you have a 4 by 4, then it's going to be 1, -1, 1, -1, -1, 1, -1, 1. So it's like a chessboard. Black, white, black, white, black, white, black, white. So it's always like this. All right, so -1 times the determinant of for, yeah, let's just take everything and then delete stuff. It's easier. So I delete, it's 2, so I delete the first column, first row and the middle column. +1 time, plus, oh yeah, no, that's 2, sorry. Yeah, -1 times 2 times this, +1 times 5 times the determinant of, now it's 5, so I just delete the center column and the center row. And then -1 times 8 times the determinant of this last matrix there. So here it's 8, so I get rid of this row and the center again. And if I compute it, somebody have an intuition of what I might get? Personally, I didn't when I first computed it. Well, let's first do it completely. So here I get -2 times 4 times 9 minus 7 times 6. Here I +5 times 1 times 9 minus 7 times 3. And then -8 times 1 times 6 minus 4 times 3. And if I compute this, I get, oh, I get 46. Oh, here I get, it's 4 times 9, yeah. So see, it's possible to make a mistake. Oh, -24, that's not what I thought I would get either. Let me compute the determinant. Yeah, it's 0. Yeah, okay, so the right answer is 0, so I made a mistake somewhere. Okay, it's -2 times 4, 6, 7, 9, plus 5 times 1, 9, 7, 3. That's -8 times 1, 3, 4, 6. Yeah, so 4 times 9 minus 7 times 6 plus 5 times 7 times 3. No, I think it's -5. It's +5, yeah. It's plus, minus, plus, minus, plus. So it should be plus, yeah, +5 times 1 times 9 minus 7 times 3 minus 8 times 1 times 6 minus 4 times 3. Oh, it looks like there's no mistake, but what am I missing there? Yeah, no, it's equal there. It's either I proceed this way or I can proceed that way, for instance. Okay, let's do it by hand. So 36 minus 42, 42, yeah. 9 minus 21, 6 minus 12. Yeah, it's supposed to give 0. So 36 minus 42, that's yeah, minus 6. So 12. 5 minus 21, that's minus 12. So minus 60. Then 6 minus 12, minus 6. So plus 48. So 48 plus 12 is 60. Yeah, okay, it's 0. All right. Okay, that's what I had found. Yeah, it's just my computer. So maybe it was not liking when oh, maybe it didn't like. Maybe I should have written this way. This is what I've liked. Yes, all right, okay, that was the problem. Okay, so what do we conclude about this?
Well, because it's the determinant is equal to 0, the inverse is undefined, so it doesn't exist.
Yes. So it is singular. Its inverse is undefined. But so finding the reason isn't all that easy. So challenge, find how the rows columns are linearly dependent. All right. Additional properties of the determinant. The determinant is unique. Yeah, a non-zero determinant implies linear independence. The determinant of A equals the determinant of A prime or A transpose. Oh yeah, I already, yeah, so I already gave you all these properties for 2 by 2, but they are also true for n by n. Yeah, so if 2 rows or columns are interchanged, the sign changes. If every value of or column is multiplied by a constant, the determinant is multiplied by that constant. The addition or subtraction of a multiple of any row, column, from another does not change the determinant. And then condition for non-singularity. Squareness. Yeah, I'm kind of restating the same thing. It's just in a more structured way, and linear independence of rows or columns. Then, yeah, no, I'm not going to write other things. All right, so to verify, here, independence, we can find what we call the row echelon form of a matrix. What is row echelon form? So row echelon form looks pretty much like what you would do when you are trying to solve a system of linear equations. So imagine I give you this system. So what are you going to do? Well, you're going to say, oh, let me find x in terms of y and z, and then I can substitute this value of x in the second and the third, and I can just have a solution in terms of y and z in the second and y and z in the third. Then I can find y in terms of z and substitute it in the last one. So what are you doing there? You're at every step, you're eliminating one of the variables. So essentially, this is the principle behind the row echelon form, is we're going to build a matrix of a system of linear equation that's equivalent to the general one, but in which we have fewer and fewer non-zero coefficients as we go down the number of equations until we have just zeros. So I'm going to tell you exactly how we do it. So the row echelon form is each row I of a matrix in a row echelon form has at least I minus one leading zeros. So the first one has no leading zeros, but then the second one has one leading zero, and then the third one has two, or at least. each row must at least one more leading zero than the previous one. So, and lastly, the first non-zero element of each row is called a pivot. Also note, non-squared matrix may also be put in row echelon form. Yeah, sorry, that's a lot of statement definitions, but yeah, I'd like to do it for one, at least one matrix before we leave. Since you don't have a TA session right away, it's going to be recorded. So I can just maybe go 5 minutes over just to show you what is a row echelon form. Yeah, to do so.
Sorry, Professor, you said that we don't have a tutorial today?
Yeah, it's so yeah, I don't want to tell you like the details of what happened, but basically, yeah, so it's just going to be recorded later today, or maybe or very soon. But I already posted the solutions of the TA sessions, and if for whatever reason you watch the video and you look at the solutions and you're confused, just ask me and I'll have a or come to the office hours, or just write me an email and I can schedule a time to chat with you and explain you if you have any problem with the exercises.
Okay, thank you.
Yeah, it's sorry about that. It's a miscommunication, and yeah, that happened. Okay, so we use what we call Gauss-Jordan elimination. Jordan, I don't really know who that is, but Gauss was, yeah, probably the best German mathematician of all time. Very famous, very awesome person. So what you can do is one, interchange one row of the matrix with another matrix, and two, replace one row with that row plus or minus constant times any row of that matrix, including itself. So I could just have written a third rule. You can multiply or divide a row by a constant, but this is just encompassing the same thing. All right, so let me show you what this means. So just before we leave, so example, A1 equals, so what we had, let's use the same example as before. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So then what I'm going to do is I want to put zeros there. First of all, I'm going to use the first row to put a 0 here and a 0 there. And all I can do is interchange the rows and replace one row with plus, minus, another plus a constant. So let's first add -4 times the first row to the second row, and -7 times the first row to the third row. So you see that if I multiply this by -4, I get -4, -8, -12. But then I'm going to have 4 minus 4, 0 here, and that's what I'm after. So so I'm going to add -4 times row 1 to row 2, and add -7 times row 1 to row 3. So I'm going to get, note that it's a different matrix, so I'm just going to write it A2. So here it's -4, -8, -12. This is -7, -14, -21. So I get 0, -3, -6, and I get 0, -6, -12. And then what I can do is add -2 times row 2 to row 3. I would get A3 equals 2. 0 times -2 is 0. So +6 here, and -2 times row 2, so +12. And I get what? I get 0, 0. So that's an accident. I would have preferred to have not a 0 there, because that would have meant that my system is non-singular, is good. But is it surprising that I get a 0 there? Well, no, because I already found out that when I computed the determinant of this matrix, I got 0. So I already know that the inverse is undefined and it's the matrix is singular. And this is another way in which I see it. So it's exactly the thing I would have gotten if I had tried to solve the system based on the matrix with these coefficients. I would have found that at some point one equation goes away when I try to eliminate it with the other ones. Hence, the last row was indeed collinear, dependent, with the two others. And then last concept before leaving, the rank of the matrix is the number of independent rows. So it is 2. And when a 3x3 matrix has 3 independent rows, then we see that it is full rank. And when it doesn't have, here it doesn't have, it's just 2 independent equations, then we see that it's rank deficient or not full rank. And that's when we're in trouble. Okay, so we're out of time. So I think you can do quite a lot of, yeah, next time I'm going to talk more about the ranks of matrices and stuff like that, but you're quite good to go with the next TA session, the next exercises. And yeah, sorry about, again, about the TA session today. All right, any question before we leave? I know I went fast here. It's mostly mechanical, so I just wanted you to see how things are done. So if you need to find the rank of a matrix, you know how to do it. So you find it's a row echelon form. And then, yeah, next time we're going to dig deeper into how you compute inverses. So any questions before we go?
Will you be posting the solutions to the assignment?
Yes, of course. Yes. That's the whole point. Yeah, it's just today. We next time it's going to be a normal TA session.
Professor, I had a question concerning the exam.
Yeah.
Did you have a bit more information in terms of the format? I know it says it's timed, but what specifically could that mean?
Okay, it's just so I'm the one who decides everything. So, so what I was planning on doing is I'm going just to write down the questions, and then I post them on Moodle at some moment. So it's like if you have some assignment and you have some time to hand in the assignment. So there's some time, and at the end you have, of course, you have a bunch of time, and for people who have who need more time, you are allotted more time, and so at the end you have to scan your solutions, and upload them online.
Okay. So it's not like my question is more like it's not a kind of a 2-hour timed exam. Like, is it actually a take home, or are we like
Yeah, no,
I'm just trying to understand. Yeah.
It's not a take home. It's at some point the exam appears on Moodle. You get some time to do it, and then but it's yeah, it's like a take home, but a very short take home. You get like not so much time. I don't know if I wrote how long it was, or
No,
yeah.
exactly.
So I'll tell you later. But yeah, maybe half a class. I don't know. I'll see, or maybe an entire class. Depends.
Okay.
Yeah, I'm not completely settled yet on that. Any other questions? All right, so thanks everyone, and I see you next week.
Thank you.